Right now, billions of frozen worlds are circling the sun beyond Neptune. Some are as big as cities, some are as big as states. One is bigger than Pluto, and we have visited almost none of them. The Kuiper belt stretches nearly 2 billion miles wide, and something inside it is bending the laws of physics as we know them. Scientists think a hidden planet the size of Neptune is pulling objects from the dark. We will go from Pluto's frozen mountains to ancient red worlds, to a mystery that may rewrite the solar system entirely. If you enjoy the journey, drop a like and subscribe. Strap in. We begin. Most people draw the solar system like this: Sun in the middle, 8 planets in neat rings around it, Neptune on the edge, then nothing. That picture is wrong, and the part they left out is the most terrifying part of all. Past Neptune, starting at roughly 2.8 billion miles from the Sun, a massive ring of frozen objects circles our star. Billions of them, some the size of mountains, some the size of states, some possibly the size of small planets we have not yet found. This ring is called the Kuiper belt, and it is not empty, dead, or quiet. It is crowded, ancient, and strange beyond anything most people ever hear about. Here is the part that should bother you. The Kuiper belt does not start far away. On a solar system map, it begins right where Neptune's orbit ends. Neptune is already 3 billion miles from the Sunday. That already feels impossible to imagine, but the Kuiper belt extends from there outward for another 1.5 billion miles. If you drove a car at 60 miles an hour without stopping, it would take you over 3 million years to cross it. And here is the thing that makes scientists lose sleep. We have explored almost none of it. We have sent spacecraft to Mars. We have landed robots on an asteroid. We have even crashed a probe into a comet. But the Kuiper belt is so far away and so vast that we have done a full flyby of exactly 2 objects inside it. 2 out of billions. Every object sitting in that ring right now is a frozen piece of the original solar system. Nothing has melted them. Nothing has broken them down. They have been sitting out there, perfectly preserved, since before Earth existed, since before the Sun was even a real star. They are time capsules from the moment of creation, drifting in the dark. And the dark out there is complete. Sunlight at that distance is so faint it would be like trying to read by a candle from 2 football fields away. The temperature drops to around 360 degrees below zero. At that temperature, gases that flow freely here on Earth freeze solid into rock-hard ice. Now, imagine billions of those frozen objects, many the size of small towns, silently orbiting the Sun in that blackness. Some of them are on stable paths they have followed for 4 billion years. Others are getting nudged. Their orbits are shifting. Something is pushing them. Scientists have been trying to figure out what for decades, and the answer they keep coming back to is deeply unsettling. But before we get to that, you need to understand exactly how this belt was discovered, because the story of how we even knew it existed before we could see it is one of the strangest moments in science history. Here is the wild part. For years, the Kuiper belt was just math on paper, a prediction, a calculated guess. No one had seen a single object inside it, and yet 2 scientists, working separately, looked at the data and told the world, something enormous is out there. They were right. And that moment changed everything we thought we knew about the edges of our solar system. What pushed them to make that call is what comes next. In the 1950s, a Dutch astronomer named Gerard Kuiper sat down with a pencil, some math, and a problem that nobody else thought was worth solving. The problem was this: where do comets come from? Comets streak through our sky every few years. They leave glowing tails of gas and dust. They have been doing this for as long as humans have looked up, and for just as long, nobody questioned where they started. They just appeared. They burned bright. They vanished. End of story. Kuiper looked at the math and found that story incomplete. Comets lose material every time they pass the Sunday. They shed ice and gas like a candle burns wax. A comet that visits the inner solar system too many times eventually falls apart. So the comets we see today cannot be billions of years old. They must be coming from somewhere. Something must be feeding them into the inner solar system on a steady schedule. He ran the numbers. He looked at orbital speeds, distances, the age of the solar system, and the rate at which comets decay, and he concluded that there had to be a reservoir, a storage zone, a frozen field of objects beyond Neptune that occasionally bumped a chunk of ice inward toward the Sunday. He published his idea and mostly got ignored. Then, in 1992, a team of astronomers aimed a telescope at the sky beyond Neptune and found it. One small, frozen object, reddish in color, drifting in exactly the region Kuiper had described. They called it 1992 QB1. It was about 100 miles wide, nothing dramatic, but the confirmation was electric. Within months, more objects appeared, then hundreds, then thousands. The Kuiper belt was real. The math had been right all along, and it opened a much bigger question. If this many objects were sitting out there, and nobody had predicted their full scale, what else were we missing? Here is the part that should make you pause. Kuiper's prediction was based on comets alone. Short-period comets, the ones that circle back to the inner solar system in less than 200 years, came from his belt. That prediction was correct, but scientists soon realized the Kuiper belt was far larger, far more populated, and far stranger than he ever imagined. The objects out there were not just comet seeds. Many were enormous. Some were hundreds of miles across. Some had moons. At least one had a thin atmosphere. And all of them were frozen so completely that they preserved chemical signatures from the birth of the solar system itself. Kuiper had found the tip of something massive, something that would take decades more to even begin to understand. And the next object that pushed our understanding over the edge was one the entire world already knew by name. It had been called a planet for 76 years. It had been in schoolbooks, on maps, in cartoons. But when scientists looked at it through the lens of what they now knew about the Kuiper belt, they realized it had been misclassified the whole time. And fixing that mistake revealed something much larger and far more alarming about the chaotic neighborhood it called home. That object, and what stripping its title exposed, is where the story gets much harder to ignore. Picture a ring around the Sunday, not a thin line, a wide, thick band of space, filled with billions of frozen objects, all orbiting slowly in the darkness beyond Neptune. That ring is the Kuiper belt, and the moment you understand its actual size, everything you thought you knew about the solar system shifts. The Kuiper belt stretches from roughly 30 times the Earth-Sun distance out to about 50 times that same distance. To put that in miles, it occupies a zone that spans more than 1.5 billion miles of space. For comparison, the entire distance from the Sun to Neptune is about 2.8 billion miles. The Kuiper belt itself is a structure that rivals the width of the entire inner solar system. Inside that ring, scientists estimate there are at least 100,000 objects larger than 60 miles across. That is 60 miles in diameter, larger than the entire city of Los Angeles spread edge to edge. And those are just the ones big enough to detect with current technology. The number of smaller objects, ones the size of towns or neighborhoods, runs into the billions. Each one of those objects is a frozen world. Some are pure ice. Some are rock wrapped in ice. Some have layers of frozen methane, ammonia, and water stacked on top of each other like a geological sandwich built by 4 billion years of cold. They do not sit still. Every single one orbits the Sunday, but their orbits vary wildly. Some travel in nearly circular paths. Others are tilted at extreme angles to the flat plane where the planets orbit. A few have been nudged into paths so stretched and elliptical, they swing far beyond the main belt before looping back. No two objects in the Kuiper belt travel the exact same route. Scientists call the most stable group the classical Kuiper belt objects. They orbit in a relatively calm band and have been there since the solar system formed. They are the quiet ones. Then there are the resonant objects, those whose orbits lock into a mathematical rhythm with Neptune's gravity, like dancers matching a beat. Pluto is one of these, completing 2 orbits for every 3 Neptune makes. Then there are the scattered ones, objects that got thrown into wild, tilted paths by gravitational nudges from the giant planets. These are the ones most likely to eventually get kicked inward toward the Sun, turning into the comets we see blazing across our sky. This is the part that stops most people cold. The sheer number of objects in the Kuiper belt means the inner solar system has been bombarded throughout history. Comets that have struck Earth, that may have brought water, that may have seeded the chemistry for life, came from this frozen ring. Everything in that belt is a potential projectile aimed at the planets inside it, including ours. And the question of what controls these trajectories, what nudges objects out of stable orbits and sends them spiraling inward, leads to something that rewrote the history books. Because the answer was sitting in plain sight, right at the beginning of the Kuiper belt itself, wearing a name most people recognized. What happened when scientists finally looked at Pluto clearly is a story nobody was prepared for. For 76 years, Pluto was a planet. Simple as that. Kids learned it in school. It showed up on every solar system poster, hanging at the edge of the known world like a lonely frozen outpost. Then, in 2006, everything changed. Pluto lost its title. Overnight, it became something called a dwarf planet. The public was furious. Scientists argued. Petitions circulated. Some people still refused to accept it. But hidden inside that argument was a discovery that mattered far more than any title. Pluto's demotion was not about Pluto. It was about what surrounded it. The problem started in 2003, when a team led by astronomer Mike Brown spotted an object beyond Pluto. It was roughly the same size. Some measurements suggested it might even be slightly larger. Scientists called it Eris, after the Greek goddess of strife. That name turned out to be fitting. Eris caused a fight that lasted years. If Pluto was a planet, Eris had to be one too. And if Eris was a planet, then the dozens of similar-sized objects scientists were already finding in the outer solar system would all need the same title. The solar system would suddenly have 15 planets, maybe 20, maybe more, as telescopes improved. So scientists faced a choice. Either they accepted a solar system with an ever-growing list of planets, or they created a new category. They chose the new category. Pluto, Eris, and objects like them became dwarf planets, a class defined by being round, orbiting the Sun, but sharing their neighborhood with other similarly sized bodies. That phrase, sharing their neighborhood, is the key. And that key unlocked something alarming. Pluto does not sit alone in the outer solar system. It lives in a crowd. The Kuiper belt, the region Pluto calls home, contains thousands of objects of comparable size. Some are hundreds of miles across. Some are covered in the same reddish material as Pluto's surface. Some have moons of their own. The reclassification forced scientists to ask a question they had been avoiding. How many large objects are actually out there? The answer they got back was uncomfortable. Surveys using powerful telescopes revealed the Kuiper belt was even more densely populated than anyone had calculated. And the more they looked, the stranger the population became. Objects were orbiting at angles that made no sense. Others were clustered together in ways that defied probability. The distribution of Kuiper belt objects, the way they were grouped and tilted, screamed that something was organizing them. Something big was out there, just beyond the range of our best telescopes, pulling strings. Pluto's demotion had ripped open the curtain. Behind it was a region of the solar system so crowded, so chaotic, and so clearly shaped by forces scientists had not yet identified that it changed the entire research agenda for planetary science. And every object sitting in that crowd carries a secret even older than the chaos itself, frozen into the chemistry of its ice. What those ancient ingredients actually are, and why they matter for life on Earth today, is stranger than anyone expected. Every object in the Kuiper belt is old. That word does not come close. These are objects that formed before Earth existed, before the moon existed, before the sun had even finished igniting into a full star. They formed 4.5 billion years ago from the same spinning cloud of gas and dust that built the entire solar system. And since that moment, they have barely changed. On Earth, time destroys everything. Wind carves mountains down to plains. Oceans reshape coastlines every century. Volcanoes bury old surfaces under fresh rock. Even the oldest stones on Earth have been crushed, melted, recycled, and reformed dozens of times over. Nothing on our planet looks the way it did 4 billion years ago. In the Kuiper belt, there is no wind, no oceans, no volcanic heat. The temperature barely rises above 350 degrees below zero, even during the part of each orbit closest to the Sunday. At that temperature, chemical reactions slow to nearly nothing. Objects simply sit, they preserve. Scientists call Kuiper belt objects pristine. That word in science means untouched, unaltered, original. These frozen bodies are the only material in the entire solar system that still looks the way the solar system did at the very beginning. Every piece of rock, ice, and frozen gas out there is a direct sample from the birth event. That is why scientists are desperate to study them. When a comet from the Kuiper belt falls into the inner solar system, it is not just a pretty light show. It is a message from 4.5 billion years ago, written in chemistry, arriving in our sky. When its surface heats up and releases gases, those gases carry information about what conditions were like before Earth had even formed a solid crust. A team of researchers studying Kuiper belt comets found amino acids inside them. Amino acids are the building blocks of proteins. Proteins are how life builds itself. The fact that these molecules exist inside frozen objects that formed before life on Earth began raises a question that nobody has answered. Did life here start with ingredients that fell from the Kuiper belt? That question is still open, and it gets more intense the deeper you look. Some Kuiper belt objects have complex organic molecules locked inside their ice. Organic molecules are carbon-based compounds, the same class of chemistry that makes up every living thing on Earth. The Kuiper belt is not just a ring of frozen rocks. It is a deep freezer full of the raw materials of life, preserved in a state older than our planet itself. And here is the part that really pulls the floor out from under you. Scientists believe the Kuiper belt today is a fraction of its original size. Something stripped away most of its mass billions of years ago. What remains is just a remnant, a leftover. If that stripping event had not happened, the amount of ancient chemistry raining down on the early Earth would have been staggering. What it was actually made of, in detail, down to the specific molecules frozen inside each object, takes the story somewhere completely unexpected. The chemistry of the Kuiper belt, once you look closely, reads like a recipe, and you will not expect what it is a recipe for. Crack open a Kuiper belt object, and you would find layers, not like the layers of Earth with its molten core and rock mantle. More like a frozen lasagna built by 4 billion years of extreme cold, stacking different kinds of ice on top of each other until they fused into a single body. The outermost layer on most Kuiper belt objects is called a mantle of processed organic material. The word organic here means carbon-based, and processed means it has been altered by something. That something is radiation. Cosmic rays, high-energy particles flying in from across the galaxy, have been bombarding these surfaces for billions of years. When those rays hit ice containing simple carbon molecules, a chemical reaction happens. New, more complex molecules form. Over time, the surface darkens into a reddish or brownish crust. That dark crust is hiding something underneath. Beneath the processed surface layer, scientists believe there is a zone of relatively fresh ice, shielded from radiation by the crust above it, and beneath that, a core of denser rock mixed with ices. The ices themselves are the strange part. Water ice is in there, the same kind that fills Earth's oceans. But that is just the start. Methane ice sits alongside it, frozen solid at temperatures so low they are hard to even describe. Methane on Earth is a gas at room temperature. Out there, it is rock solid, locked into the body of these objects for billions of years. Ammonia ice is in there too. Carbon monoxide ice, carbon dioxide ice. Each one frozen well below any temperature that exists naturally on Earth's surface. When a Kuiper belt object gets knocked into the inner solar system and approaches the sun, these ices start to warm. They skip from solid directly to gas, a process called sublimation. The gas bursts off the surface and carries dust with it, creating the glowing tail we call a comet. That tail is literally the interior of an ancient Kuiper belt object evaporating into space. Scientists who analyzed comet dust brought back to Earth by a sample return mission found something that stopped them cold. Inside the dust were glycine molecules. Glycine is the simplest amino acid that exists. Amino acids are the exact molecules that living cells use to build proteins. Finding glycine inside a comet, a frozen Kuiper belt object that formed before Earth's oceans existed, suggested that the chemistry of life does not need a planet to start. It can assemble inside frozen space rocks. That discovery led to a hypothesis that a serious fraction of the scientific community now entertains. Early Earth was hammered by comets from the Kuiper belt. Those comets carried water. They also carried amino acids, carbon compounds, and possibly even more complex organic molecules. Life on Earth may have received its starter kit from the Kuiper belt. If true, that means we are all, in some sense, made of material from the frozen edge of the solar system. Our biology, our oceans, possibly even the first spark of life, may have arrived from out there. That thought is large enough on its own. But the actual orbits of these objects, how they move, where they travel, and why some of them end up aimed directly at Earth, is a puzzle that goes even deeper than the chemistry. And some of those orbits make absolutely no sense at all. An orbit should be predictable. The sun pulls everything toward it with gravity. Objects move around it in set paths, like runners on a track. With enough data, scientists can calculate exactly where any object in the solar system will be 1,000 years from now. That system works perfectly for the planets. In the Kuiper belt, it breaks down. Most Kuiper belt objects do orbit the sun in fairly regular paths, but a significant group of them move in ways that follow no clean pattern. Their orbits are tilted at extreme angles to the flat plane where the planets travel. Some are so tilted they orbit nearly perpendicular to everything else, like a wheel rolling sideways. Others follow paths that stretch so far from the sun that they spend most of their time in darkness so complete it makes the Kuiper belt itself look warm and bright. What makes this strange is that gravity, in theory, should have sorted these objects into orderly patterns long ago. The solar system is 4.5 billion years old. Over that span of time, gravitational interactions should have nudged chaotic orbits towards something more regular. The fact that so many Kuiper belt objects still travel in wildly tilted, wildly stretched paths means something is actively maintaining that chaos. Something is keeping their orbits disturbed. The leading candidate is Neptune. The giant planet's gravity reaches out into the Kuiper belt like a conductor keeping the section in rhythm. Many Kuiper belt objects are locked in what scientists call orbital resonances with Neptune, meaning they orbit the Sun in a neat mathematical ratio compared to Neptune's own orbit. Pluto, for example, completes exactly 2 orbits for every 3 that Neptune completes. That ratio keeps them from ever getting too close to each other, like 2 runners on the same track who always stay safely apart. But resonance with Neptune does not explain the extreme cases. Some objects have orbits tilted at 40 or 50 degrees. Others have orbital paths that take them so far beyond the main belt that Neptune's gravity becomes nearly irrelevant at their farthest point. And a handful of objects cluster together in ways that should be statistically impossible if only Neptune were involved. In 2016, 2 astronomers named Konstantin Batygin and Mike Brown ran a simulation. They fed the strange, clustered orbits of 6 distant Kuiper belt objects into their model and asked the computer what could cause them. The computer came back with an answer that made headlines around the world. The only thing that could produce those orbital patterns was another planet, a massive one, sitting far beyond the Kuiper belt, pulling objects into alignment with its gravity, not a small body. Something with a mass estimated at 5 to 10 times the mass of Earth, orbiting the Sun in a path so large that one complete trip around our star might take 10,000 to 20,000 years. Nobody has seen it, no telescope has confirmed it, but the math says it is there. And the more scientists look at Kuiper belt orbits, the harder it gets to argue that the math is wrong. What that object would mean for the solar system and why its existence changes everything from orbital mechanics to Earth's own history is the next piece of the story. And it is the one that keeps physicists up at night. Something is pulling on the Kuiper belt. Scientists can see the fingerprints of that pull in the orbits themselves, even though whatever is doing the pulling remains invisible. That is the situation planetary scientists have been living with for years, and it has produced one of the most intense debates in modern astronomy. Here is what they actually observe. A specific group of distant Kuiper belt objects, the ones with the most extreme, stretched out orbits, all point in roughly the same direction in space. Their orbits tilt and cluster as if something massive is herding them. The probability that this clustering happened by pure chance, without any force organizing it, has been calculated at around 1 in 500. Those odds are not impossible, but in science, 1 in 500 is not comfortable either. It is the kind of odds that make researchers keep looking. The clustering is not just a matter of direction. These objects also share a tilt relative to the solar system's plane. They dip below the flat disk of the solar system in a consistent pattern. To produce that kind of uniform tilt across multiple unconnected objects, you need a gravitational source. A single massive body orbiting at a steep angle to the solar plane could create exactly this effect over billions of years. The math behind this is actually elegant. A distant, massive planet orbiting at an angle would act like a slow-motion magnet on the objects nearest it. Over time, its gravity would gradually torque their orbits, pulling them into alignment. The objects would not move toward the planet. They would just begin to point at it, like compass needles orienting toward a distant magnetic north. Scientists call this the shepherding effect, and it shows up clearly in simulations. When researchers plug a massive distant planet into their computer models, the resulting orbital distribution of Kuiper belt objects matches what telescopes actually observe. When they remove the planet from the model, the match falls apart. There is one more piece that sharpens the case. Some Kuiper belt objects orbit in the opposite direction to everything else in the solar system. They circle the Sun backward, which is something gravitational chaos alone struggles to produce. A massive tilted planet, pulling on the solar system from an angle, could explain these retrograde orbits by flipping some objects over billions of years. None of this is direct detection. Scientists are reading gravity's shadow, not the source. They are like detectives finding footprints and concluding something large walked through without ever seeing the animal itself. What makes this specific investigation remarkable is who is leading it. Mike Brown, the astronomer who discovered Eris and triggered Pluto's demotion, is now the same researcher arguing most publicly that a 9th planet exists. He has spent years hunting it. His team has narrowed down the region of sky where it should be hiding. They have eliminated large sections of the sky where it is definitely absent. The remaining search zone shrinks every year, and as it shrinks, the pressure on the next chapter of this story builds. Because if Planet 9 exists, everything we think we know about how the solar system formed and why the Kuiper belt looks the way it does today has to be rewritten. That rewrite starts with a name, one that has been whispered in astronomy circles for years. The planet with no face. Give it a name and it suddenly feels real. Planet 9, a world that has never been photographed, never directly detected, never confirmed by any instrument humans have built. And yet, right now, Some of the sharpest minds in planetary science believe it exists and are actively searching for it. The case for Planet 9 rests on a collection of orbital signatures so consistent and so hard to explain otherwise that many researchers treat its existence as the most reasonable working hypothesis on the table. Here is the core argument. When scientists look at the most distant Kuiper belt objects, the ones with orbits that stretch far beyond the main belt before looping back, they find a pattern. These objects cluster. Their elongated orbits all point toward the same region of the sky. Statistically, this should not happen unless something is organizing them. The leading candidate is a planet roughly 5 to 10 times the mass of Earth, sitting in a highly elongated orbit that takes it anywhere from 200 to 1500 times the Earth-Sun distance away from our star. If that orbit sounds extreme, that is because it is. At its farthest point, Planet 9 would be so distant that the Sun would appear as little more than a bright star in its sky. Light from the Sun, which takes 8 minutes to reach Earth, would take over 20 hours to reach Planet 9 at its farthest point. It would sit in darkness so deep that no telescope currently in operation can reliably spot it. Its surface would be so cold that even frozen methane might begin to collapse into a different physical state entirely. At its closest approach to the Sun, which by some estimates happens once every 10,000 to 20,000 years, Planet 9 swings inward enough that it theoretically could be detected. But closest approach for an orbit that large still means a distance 6 times farther than Neptune. That is still deeper than anything humans have ever explored. Why has it not been found? Sky surveys take time. The night sky is enormous. To spot a cold, dark planet at that distance, you need a telescope sensitive enough to detect light that has traveled thousands of times farther than sunlight travels to reach Earth. The object reflects almost no light of its own. It is dark ice and rock against a dark sky. Finding it is like looking for a charcoal brick on a dark road at midnight with a flashlight that barely reaches 20 feet. But the search is not hopeless. Scientists have used the orbital data of known Kuiper belt objects to narrow the search zone considerably. Planet 9, if it exists, is most likely hiding somewhere in a specific band of sky. Several major observatories have begun systematic sweeps of that region. There is a competing explanation. Some scientists argue the clustering in Kuiper belt orbits could be a statistical fluke, made worse by observational bias, meaning we simply tend to observe objects in certain parts of the sky more than others. Under this view, Planet 9 is an elegant ghost, a pattern we created by not looking everywhere equally. The debate is genuinely unresolved. What nobody disputes is this: the orbits of distant Kuiper belt objects are strange. They require an explanation. Either the universe is playing a remarkably consistent statistical trick on us, or something enormous is out there in the dark. Something that formed in the inner solar system billions of years ago and got ejected outward, or something that formed far out and never came in at all. Something that has been shaping the Kuiper belt in secret since before Earth had continents. What that object would look like up close, what it is made of, and how long humans have before they find it, is the cliffhanger nobody has answered yet. But to understand why finding it matters so much, you first need to feel the actual scale of the space it hides in. And that scale is where human intuition completely collapses. Scale is the single hardest thing to communicate about the outer solar system. Numbers alone fail. When you hear 1 billion miles, your brain files it in the same folder as really far away and moves on. The Kuiper belt demands something more than that, because the distance involved is the kind that makes even trained astronomers stop and stare at nothing for a moment. Start with something familiar. The distance from Earth to the Sun is about 93 million miles. Scientists call this one astronomical unit, a shorthand for the basic measuring stick of the solar system. Earth sits at 1, Mars sits at about 1.5, Jupiter, the giant, orbits at about 5, Saturn at about 10, Uranus at about 20, Neptune, the farthest planet, sits at roughly 30. The Kuiper belt begins at 30 and ends at around 50. That means the entire span of the Kuiper belt, from inner edge to outer edge, covers the same distance as 20 Earth-Sun lengths. 20 times the distance from here to the Sun, stacked end to end, just across the belt from one side to the other. Here is a comparison that helps. If you shrank the entire solar system down so that the Earth-Sun distance was 1 inch, the Kuiper belt would stretch from 2.5 feet to 4 feet away from you. Neptune would be 2.5 feet out. The outer edge of the Kuiper belt would be at 4 feet. And the hypothetical planet 9, at its farthest point, would be over 10 feet away. In that same model, Pluto is about 2.5 feet out, barely at the inner edge of the belt. Now scale that back up to real distances. The New Horizons spacecraft launched in January 2006. It was the fastest object humanity had ever launched at that point, moving at over 35,000 miles per hour. It flew past Mars in 3 months. It crossed Jupiter's orbit in 13 months, using Jupiter's gravity to slingshot even faster outward. And it reached Pluto at roughly 30 times the Earth-Sun distance in 9.5 years. 9.5 years at 35,000 miles per hour just to reach the inner edge of the Kuiper belt. At that same speed, crossing the full width of the Kuiper belt would take an additional 3 years or more. And reaching the outer fringes, where objects like Sedna and the hypothetical Planet 9 reside, would take decades beyond that. The Kuiper belt is enormous in a way that has practical consequences. Scientists cannot simply point a spacecraft at a random Kuiper belt object and go study it. By the time a mission could be planned, funded, built, launched, and actually reach a target, the scientists who designed it might be retired or gone. The lead researcher on the New Horizons mission, Alan Stern, spent decades fighting to get that spacecraft funded and launched. He was in his 40s when it launched. He was in his 50s when it reached Pluto. And New Horizons only visited one major object in the belt. The scale of the Kuiper belt is why so much of it remains unknown. The vastness is the obstacle. But for all of that, when New Horizons finally got there and sent back its first images of Pluto, what scientists saw waiting for them at the inner edge of that belt stopped the entire planet cold. What Pluto actually looked like up close was something nobody had predicted. On the morning of July 14th, 2015, the New Horizons spacecraft slipped past Pluto at 31,000 miles per hour. It had no brakes. It could not slow down or stop. It had exactly one chance to take every measurement it needed before flying past into the darkness beyond. The team back on Earth held their breath. The spacecraft was so far away that radio signals, even moving at the speed of light, took 4.5 hours to make the one-way trip. If anything went wrong during the flyby, scientists would not know about it until hours after the moment had already passed. There was nothing anyone could do in real time. The spacecraft was completely on its own. New Horizons had traveled 9.5 years to reach that moment. During that journey, it crossed every planet's orbit, threaded the asteroid belt, slingshot around Jupiter, and spent years in cruise mode with most of its systems shut down to conserve power. It was the fastest spacecraft ever launched, and it still needed almost a decade to cross the distance separating Earth from Pluto. To help visualize that journey, consider this. If you drove from Los Angeles to New York at 60 miles per hour, non-stop, it would take you roughly 46 hours. Scaling that drive to match New Horizons' journey, it would be like driving that route every single day for 9.5 years. The distances involved are simply on a different level than anything that fits in daily human experience. The spacecraft itself was small, roughly the size and shape of a grand piano, about 1,000 pounds, crammed with scientific instruments and an antenna the size of a large satellite dish. It ran on nuclear power generated by the decay of plutonium, because sunlight at that distance is too faint to run solar panels reliably. During the flyby, New Horizons had less than 24 hours in Pluto's close vicinity. Its cameras, spectrometers, and dust detectors fired constantly, recording everything they could. But the spacecraft's antenna could only point in one direction at a time, and to collect data, it had to face Pluto, not Earth. So during the actual flyby, New Horizons went silent from Earth's perspective. Scientists got no data in real time. They waited. 14 hours after the closest approach, New Horizons pivoted its antenna toward Earth and sent a single short confirmation signal. It had survived. The room at Mission Control in Maryland erupted, but the actual images and data took over a year to download in full. The spacecraft's radio transmitter was so weak and the distance so vast that the data trickled back at a rate slower than an old dial-up internet connection. What arrived in those transmissions reshaped planetary science. The images showed mountains, real, solid mountains made of frozen water ice, rising over 11,000 feet above Pluto's surface. That is taller than any mountain in the American Rockies. And they were geologically young, barely 100 million years old, meaning the surface of Pluto had been actively reshaping itself. Out there, in the deep cold, something was driving geological activity, and surrounding those mountains was a feature nobody predicted: a vast, flat, pale plain shaped unmistakably like a heart. It covered an area roughly the size of Texas. Scientists named it Tombaugh Regio, after Clyde Tombaugh, who discovered Pluto in 1930. What created it, how it formed, and why it was smooth while everything around it was rugged and cratered, sent scientists back to their models with questions they are still answering today. The answer pulled them much deeper into the Kuiper belt, toward an even stranger world waiting farther out. The first full image of Pluto dropped into the world's news feeds on July 14, 2015, and the reaction was immediate and universal. That is a real world. Before New Horizons, Pluto was a blurry smudge in even the most powerful telescopes. The Hubble Space Telescope, the sharpest eye humans had ever pointed at space, could only resolve Pluto into a rough blob of light and dark patches. Scientists knew it had a large moon, a thin atmosphere, and a surface that appeared to change color. That was almost everything. The first high-resolution image changed the category entirely. Pluto was alive, geologically active, dramatically varied in texture and color, and sitting at the center of that first image was the heart. The heart-shaped region, officially named Tombaugh Regio, is a bright plain of frozen nitrogen ice roughly the size of Texas and Oklahoma combined. It sits in a low basin. Nitrogen ice flows into it from surrounding highlands like a very slow glacier, filling the basin from the edges inward. At the surface, this ice constantly cycles. Nitrogen freezes on the night side, sublimates to gas on the day side, moves through the thin atmosphere, and refreezes elsewhere. Pluto breathes, in a way, slowly, over centuries, but it breathes. The mountainous terrain bordering the heart is a different story. Those mountains are made of water ice. Frozen solid at 370 degrees below zero, water ice at those temperatures behaves like rock. It is rigid, structural, capable of holding a mountain's weight for billions of years. The peaks rise over 11,000 feet above the surrounding plains. For context, that is higher than the tallest mountains in the continental United States, and they appear to be geologically young, maybe only 100 million years old, meaning Pluto has experienced mountain-building activity relatively recently in planetary terms. Here is the part that puzzled scientists the most. What is powering that geological activity? Pluto has no nearby massive planet pulling on it with strong tidal forces, the mechanism that drives volcanic activity on some of Jupiter's moons. It has no internal heat source scientists can easily identify, and yet its surface shows clear signs of ongoing change. Possible ice volcanoes, recent surface features, a geologic history that does not look 4.5 billion years old. One idea gaining ground is that Pluto may have a liquid water ocean deep beneath its icy surface. The freezing and pressurizing of that hidden ocean could generate enough heat and movement to reshape the surface from below. If true, It would mean Pluto, sitting at the edge of the solar system in near total darkness, hosts liquid water. That detail hits differently when you remember that liquid water is the single environmental requirement that life on Earth cannot do without. New Horizons also found mountains with flat tops, possible evidence of ancient ice volcanoes that erupted slush instead of lava. It found dunes of frozen methane, sculpted by winds barely strong enough to be called winds. It found a layer of blue haze hovering above the surface like a thin, smoggy sky. Every discovery raised more questions than it answered, and the spacecraft did not stop at Pluto. It kept flying, deeper into the Kuiper belt, toward a target so small and so far away that even finding it had required one of the most ambitious telescope searches in history. What waited at that next stop was unlike anything New Horizons had prepared scientists to expect. After Pluto, New Horizons kept moving. It had no choice. At 31,000 miles per hour, with no braking system, it was aimed outward into the Kuiper belt, and it was going there regardless. But scientists had a plan. While the spacecraft was still years from Pluto, a team had begun searching the Kuiper belt for a reachable target beyond it. Finding one was harder than it sounds. New Horizons was already flying in a specific direction determined by its launch trajectory. A new target had to be something the spacecraft could actually reach with its remaining fuel supply, meaning it had to fall within a narrow cone of accessible space in the direction New Horizons was already headed, and the target had to be large enough to study, but far enough out to make the trip worthwhile as a scientific extension. The team used the Hubble Space Telescope to scan the sky ahead of New Horizons and found several candidates. They picked the best one. A small Kuiper belt object sitting roughly 4 billion miles from the Sun, about 1 billion miles beyond Pluto. Scientists gave it the nickname Ultima Thule, an ancient Latin phrase meaning beyond the known world. After the flyby, it was formally named Arakoth, a word from the Powhatan language meaning sky. New Horizons reached Arakoth on January 1st, 2019. The images it sent back were unlike anything anyone had predicted. Arakoth is shaped like a snowman. 2 rounded lobes connected at a narrow neck, one lobe noticeably larger than the other. The total length of the object is about 22 miles from tip to tip, roughly the length of Manhattan Island. Its surface is red, deeply so, colored by billions of years of radiation turning simple carbon molecules into complex, dark organic material. But the shape is the story. The 2 lobes of Arakoth were once separate objects, 2 small bodies, formed independently in the same region of the Kuiper belt, that drifted together so gently they barely touched before gravity held them against each other. Scientists call this a contact binary. It means the 2 pieces merged without a violent collision. There was no crash, no explosion, no debris field, just 2 neighbors slowly touching. That gentle merger is a window into how planets form. Current models of planetary formation involve small objects sticking together, growing larger over time through a process called accretion. For decades, scientists debated whether this process was violent or gentle. Arakoth answered that question. At least for early-stage formation in the outer solar system, the process was quiet, calm. Objects clumped together slowly, like dust balls gathering on a still floor. That discovery reshaped the leading theory of how the solar system's outer bodies assembled themselves. And it came from a 22-mile wide snowman-shaped object sitting 4 billion miles from Earth, visited by a spacecraft the size of a piano, moving at more than 30,000 miles per hour. Arakoth also had almost no craters. In a region of space filled with billions of objects that should theoretically be hitting each other constantly, Arakoth's surface was smooth and unmarked, which immediately raises the next question. If the Kuiper belt is so crowded, why are objects out there not colliding constantly? And the answer to that question is more complicated than expected, and it leads directly to the reason Earth has been hit so many times throughout its history. The Kuiper belt is not a demolition derby. Objects out there are spread across a volume of space so enormous that most of them never come close to each other. The distances between individual objects, even in this belt with billions of members, are typically millions of miles. Arrokoth's nearly crater-free surface is proof that direct collisions are rarer than the population count might suggest. But rare and never are two different things. Collisions do happen. When two Kuiper belt objects slam into each other, the results can be extreme. The energy released in a high-speed collision between two frozen bodies, the size of mountains, is comparable to nuclear explosions, not in heat, but in raw, destructive force. Both objects can shatter. The debris scatters across space in expanding clouds. Smaller fragments get nudged by the collision into slightly different orbits. Then, Neptune's gravity grabs some of those fragments and tugs them further. Over thousands and millions of years, some of those fragments migrate inward. That inward migration, traveling across the solar system from the outer belt toward the Sun, is exactly how short-period comets form. A chunk of ancient Kuiper belt ice, broken free by a collision and slowly shepherded by Neptune's gravity, falls into an elliptical path that eventually brings it close enough to the Sun to heat up. Its ices sublimate. It grows a glowing tail. It becomes one of the comets humans have watched crossing the night sky since the beginning of recorded history. Every famous comet that visits Earth on a schedule of less than 200 years started as a piece of the Kuiper belt. Comet Halley, which returns every 75 to 76 years and has been recorded in human history going back over 2,000 years, originated in the outer solar system. The comets that streaked over medieval Europe and were taken as signs from the heavens were broken fragments of ancient frozen Kuiper belt material, drifting inward on journeys that took millions of years to complete. And here is the detail that changes how you see Earth's history. Comets have hit Earth multiple times, massively. Scientists examining craters on the Moon, which has no erosion to erase the record, have identified periods in Earth's early history when the bombardment rate from space was far higher than it is today. A period called the Late Heavy Bombardment, roughly 4 billion years ago, saw an enormous wave of impacts across the inner solar system. The leading explanation for what caused it involves Kuiper belt objects being destabilized by the migration of the giant planets. The same belt that may have delivered life's ingredients to early Earth also hammered it with devastating force. The same frozen bodies that carry amino acids also carry the kinetic energy of catastrophic impacts. The Kuiper belt has been both the source of what made life possible and a threat to its survival. It has given and destroyed in equal measure across Earth's history. The current impact rate is far lower than during that ancient bombardment, but it has not dropped to zero. Comets still arrive. Some cross Earth's orbit. Scientists track them. A Kuiper belt object aimed directly at Earth today would be among the most serious threats the planet could face. Just how serious is the kind of calculation that makes planetary defense researchers very quiet when they run the numbers? And the discovery of what some of the larger Kuiper belt objects actually look like up close added urgency to that calculation in a way nobody anticipated. Every comet that visits the inner solar system carries a label, if you know how to read it. The label is its orbital period, meaning how long it takes to complete one full loop around the Sunday. Comets that complete their orbit in less than 200 years are called short-period comets. The ones that take longer, sometimes tens of thousands of years per orbit, come from a completely different region of the solar system called the Oort cloud, sitting far beyond even the Kuiper belt. The short-period comets, the regular visitors, the ones human civilizations have tracked and feared and catalogued for millennia, come from the Kuiper belt. This was one of Gerard Kuiper's original predictions, confirmed by the orbital math of every short-period comet scientists have ever measured. Here is what happens when one of them falls inward. A Kuiper belt object, perhaps sitting in a stable orbit for 3 billion years, gets nudged. Maybe a passing larger object shifts its path slightly. Maybe Neptune's gravity tugs it into a slightly different resonance. Whatever the trigger, the object begins a migration inward. Its orbit stretches. Each pass around the Sun brings it a little closer to the inner solar system, The journey can take millions of years. The object remains completely frozen throughout, drifting through the outer solar system in silence, indistinguishable from any other chunk of ancient ice. Then it crosses the frost line, the distance at which sunlight becomes strong enough to begin warming the surface. Nitrogen ice starts to gas off first, then methane, then water ice near the Sunday. The gases carry dust and organic particles with them, streaming away from the nucleus to form a coma, a cloud of vapor surrounding the solid core, sometimes wider than the planet Jupiter. Behind it trails a tail, actually two tails. One is made of dust, curved slightly by the comet's motion. The other is made of ionized gas, blown straight back by the solar wind into a perfectly straight blue-white line pointing directly away from the Sunday. When you see a comet's tail, you are watching material that sat frozen in the Kuiper belt for billions of years, evaporating in real time. The nucleus of the comet, the solid core, is typically a few miles across, dark, irregular, spinning slowly. Its surface is covered in the same processed organic material that coats Kuiper belt objects, that dark reddish crust built by billions of years of radiation. Inside, the pristine ice layers preserve chemistry from the birth of the solar system. Scientists who have studied comet nuclei up close, including a European mission that successfully landed a probe on a comet in 2014, found surfaces stranger than anyone predicted. Boulders the size of houses, sitting on terrain as smooth as a sandy beach. Deep pits that appear to have formed when subsurface ice boiled away, collapsing the crust above it. Organic rich dark patches that absorb nearly all the sunlight hitting them. The comet that mission studied, a roughly 2.5-mile wide object, shaped vaguely like a rubber duck, was releasing roughly 220 pounds of water vapor every second at its most active. And that is a small comet. Ancient large impacts on Earth involved bodies hundreds of times more massive. Every ingredient in that evaporating water vapor, every organic molecule in that streaming tail, is a direct chemical sample from the Kuiper belt. The universe is sending us messages from its own beginning, and some of those messages carry enough force to reshape a planet. What happens when a fragment from the Kuiper belt stays in space instead of hitting anything, and drifts for millions of years in total silence, is something only the most extreme objects in the belt can demonstrate. There is a version of the Kuiper belt that most people imagine, a crowded wreckage zone, objects smashing into each other constantly, a chaotic ring of endless destruction. That version is wrong. The actual Kuiper belt is mostly empty space, punctuated by frozen objects spread so thinly that a spacecraft flying through it would be statistically unlikely to pass within 1,000,000 miles of anything larger than a grain of sand. The density comparison that scientists use is revealing. If you took every object in the Kuiper belt and spread them evenly across its volume, the average distance between objects larger than a mile across would be millions of miles. Driving from Los Angeles to New York and back is roughly 5,000 miles. That is nothing compared to the gap between neighboring Kuiper belt objects. The belt is vast, and its members are lonely. Collisions do still happen, because space is also old. 4.5 billion years is a long time. Even at very low collision probabilities, multiply that by billions of objects and billions of years, and you get collisions. Scientists estimate that within the main Kuiper belt, meaningful collisions between larger objects happen on timescales of hundreds of millions of years for any given pair. Rare, but real. When they do happen, the physics is violent in extreme slow motion. Two Kuiper belt objects, meeting at typical orbital speeds, are moving relative to each other at roughly 1 or 2 miles per second. For reference, a bullet travels about 1/4 of a mile per second. A Kuiper belt collision is like being struck by a wall of ice moving 4 to 8 times faster than a bullet, and that wall is miles wide. The resulting explosion shatters both objects into fragments. Larger pieces hold together by their own gravity. Smaller pieces scatter into the surrounding space. Some of the scattered fragments pick up just enough velocity from the collision to shift into slightly different orbits. Over time, Some of those orbits gradually change under the influence of Neptune's gravity. Millions of years pass. The fragment drifts inward. Some fragments take tens of millions of years to complete that journey from impact point to the inner solar system. Others take over 100 million years. When they finally cross into the warmer inner solar system, they become active comets. The comet streaking past Earth tonight might be a fragment of a collision that happened when the dinosaurs were still alive, or even earlier, still carrying its ancient cargo of pristine Kuiper belt chemistry after a 100 million year journey. The long travel time has one deeply strange consequence. Some fragments from Kuiper belt collisions are still in transit right now, moving slowly through the outer solar system, years or centuries from ever becoming visible to us. They are in the dark, silent, carrying the material of 4.5 billion-year-old ice toward our part of the solar system. We have no idea they are coming. What makes some of the Kuiper belt's most interesting objects even stranger is not their motion through space, but the fact that they do not move alone. Some of them carry companions, small worlds orbiting other small worlds, in the darkness of the outer solar system, caught in each other's gravity. And those companion systems revealed something about the mechanics of the Kuiper belt that no one expected to find this far from the Sunday. A moon is something we associate with planets. Earth has one, Mars has two small ones, Jupiter has dozens. The idea of a moon feels like it belongs to something large, something planet-sized, something that earns companions through sheer gravitational force. The Kuiper belt disagrees. Out beyond Neptune, in the frozen dark, objects barely 100 miles across have moons orbiting them, small worlds circling other small worlds. Some of these companion pairs are so evenly matched in size that calling one the moon and the other the parent body feels almost arbitrary. They are binary systems, two objects locked together by their mutual gravity, spinning around a shared center of mass located in the empty space between them. Scientists have found dozens of these binary Kuiper belt systems so far, and the number keeps rising as telescope technology improves. The current estimate is that somewhere around 10 to 20% of all Kuiper belt objects large enough to study have companions. In a belt containing hundreds of thousands of large objects, that means tens of thousands of binary pairs drifting through the outer solar system. The binaries come in different configurations. Some pairs have nearly equal-sized partners orbiting each other at relatively close distances. Others have one large object with a tiny moon far away, more like a captured rock than a true partner. And some have moons that orbit in unusual directions, suggesting they were captured from passing bodies rather than formed alongside the main object. How they form is a question with several competing answers. One idea is that two objects passing close to each other can bleed off enough kinetic energy through gravitational interaction to become bound to each other. This is called gravitational capture, and it requires a specific set of conditions that are rare but not impossible in the early Kuiper belt when the region was more densely populated. Another idea is that binary pairs form early, during the solar system's youth, when clumps of small particles in the original disk of gas and dust collapsed together into two objects rather than one. Both objects would then inherit nearly the same orbit, putting them naturally close to each other with very low relative velocity, making gravitational binding easy. The fact that so many Kuiper belt binaries have nearly equal-sized partners points toward that second idea. Capture events would more often produce unequal pairs, one large object snagging a much smaller passing rock. The prevalence of equal-sized partners suggests most binaries formed together from the beginning. Studying these binary systems has practical value beyond just understanding the Kuiper belt. By measuring how the two partners orbit each other, scientists can calculate the total mass of the system with precision. Mass measurements of Kuiper belt objects are otherwise extremely difficult to obtain. The binaries hand scientists a ruler, and the most famous binary system in the Kuiper belt is also the most dramatic. A system where the two partners are so close in size that both of them have been substantially reshaped by each other's gravity, where one of them has a canyon longer than the continental United States, and where the two bodies orbit each other so closely that observers from the surface of one could see the other hanging in the sky like a fixed, enormous moon. That system is Pluto and Charon, and what their relationship reveals about the mechanics of the outer solar system goes far deeper than anyone guessed. Pluto has 5 moons. 4 of them are small, irregular, and probably captured debris from the early solar system. They are interesting. They are not the story. Charon is the story. Charon is so large relative to Pluto that the two bodies do not behave like a planet and its moon. They behave like a double world. Charon's diameter is about half of Pluto's, roughly 750 miles across, compared to Pluto's 1,473 miles. For context, our moon is about 1/4 the diameter of Earth. Charon is half the diameter of Pluto. No other moon in the solar system comes close to that ratio relative to its parent. The gravitational consequence of that size relationship is dramatic. When a moon is small compared to its planet, the planet barely notices the moon's gravity. Earth wobbles slightly because of the moon, but the wobble is tiny. With Pluto and Charon, the mass ratio is close enough that neither body orbits the other in the traditional sense. Instead, both Pluto and Charon orbit a point in empty space between them, called the barycenter. That point sits outside Pluto's surface entirely. Pluto physically circles a point in space, pulled by Charon's gravity, while Charon circles the same point from the other side. They are tidally locked to each other as well, meaning both bodies rotate at the exact same rate as their orbital period. The same face of Pluto always points at Charon. The same face of Charon always points at Pluto. Someone standing on Pluto's Charon-facing hemisphere would see Charon hanging motionless in the sky, massive, filling a large portion of the view, never rising, never setting, permanently fixed in place. Someone standing on the opposite side of Pluto would never see Charon at all. New Horizons captured stunning detail on Charon during its flyby. The surface is dramatically different from Pluto. Where Pluto's heart-shaped plane glows bright white with nitrogen ice, Charon's surface is darker, grayer, and dominated by a massive canyon system that circles much of the moon's equator. Scientists call it Argo Chasma, and it stretches for about 1,000 miles, making it longer than the United States from coast to coast, and in places drops nearly 6 miles deep. For comparison, the Grand Canyon is about 1 mile deep at its deepest point. What caused Argo Chasma tells a story of ancient violence. Early in Charon's history, its interior was warmer, possibly containing liquid water. As that interior cooled and the water froze, it expanded. Ice takes up more volume than liquid water. The expanding interior had to go somewhere. It cracked the crust from the inside, producing rifts and canyons on a scale that dwarfs anything on Earth. Charon also has a dark reddish cap at its north pole. Scientists call it Mordor macula. That reddish color comes from the same radiation-driven chemistry that colors Kuiper belt objects, but with a twist specific to Charon. Methane leaking from Pluto's thin atmosphere drifts across space and gets trapped by Charon's cold polar region. Radiation then processes that methane into complex reddish organic compounds that accumulate over millions of years into a permanent dark stain. The Pluto-Charon system is a gravitational dance, frozen in the outer solar system, shaped by billions of years of mutual influence. And yet, even this double world, with its extraordinary geology and chemistry, starts to look almost familiar compared to what waits deeper in the Kuiper belt. Because some of the objects out there wear a color so extreme, so unlike anything in the inner solar system, that the first scientists to see it in detail needed a moment to verify their instruments were working correctly. The outer solar system is full of red things. Mars is reddish. Certain moons of Jupiter and Saturn carry reddish patches, but the redness of some Kuiper belt objects sits in a completely different category. These objects are so deeply, intensely red that scientists had to develop new descriptive categories to separate them from anything seen in the inner solar system. The reddest Kuiper belt objects reflect a color that has been described as ultra-red, a specific classification in planetary science reserved for surfaces where reddish coloration exceeds anything produced by ordinary iron oxide or simple sulfur chemistry. These surfaces are saturated with complex organic compounds, built up over billions of years of bombardment by cosmic radiation. Here is what creates that color, step by step. In the early solar system, Kuiper belt objects formed with surfaces covered in simple ices: water ice, methane ice, nitrogen ice, all relatively pale, similar to fresh snow. Cosmic rays, which are high-energy particles streaming from distant exploded stars, hit those surface ices continuously. When a cosmic ray strikes a simple molecule like methane ice, it breaks chemical bonds and allows atoms to recombine into more complex arrangements. Over millions of years, those complex molecules build up. They are called tholins, a term coined by astronomer Carl Sagan from the Greek word for muddy. Tholins are a family of reddish-brown organic compounds. They are dense, dark, and extremely resistant to further chemical change. Once they form, they tend to stay. On a Kuiper belt object with no geological activity to erase the surface, no weather, no erosion, tholins accumulate for billions of years, slowly darkening and reddening the surface until it absorbs most incoming light and reflects back, primarily, in the red part of the spectrum. The depth of color on the reddest Kuiper belt objects suggests their surfaces have been processing radiation continuously for the full age of the solar system. 4.5 billion years of cosmic ray bombardment, building complex chemistry layer by layer, molecule by molecule. What makes this scientifically significant is that tholins are organic compounds. Some scientists have proposed that tholins, delivered to early Earth by comets from the Kuiper belt, could have contributed to the chemical environment that preceded life. Tholins created in laboratory simulations have been shown to produce amino acids when mixed with water. The reddish skin of a Kuiper belt object may literally be a factory for life's precursor molecules, running in extreme slow motion for billions of years before being delivered to planets in the inner solar system. In 2015, New Horizons revealed that Charon's polar cap carries a concentration of tholins deposited from Pluto's atmosphere. The reddish staining was real, measurable, and precisely what the models predicted. That confirmation gave scientists more confidence in the tholin hypothesis overall. Ultra-red Kuiper belt objects cluster in a specific region of the belt. They tend to be in the classical belt, the stable inner zone, rather than the scattered objects with wild orbits. This clustering suggests ultra-red surfaces require very long periods of orbital stability. Centuries of sitting quietly in the same region, undisturbed enough for radiation to do its slow work without a collision scraping the surface clean. The scattered objects, the ones with chaotic orbits, tend to be grayer. Their surfaces get frequently reset by collisions, exposing fresh ice beneath. The ultra-red ones have been left alone long enough to build a 4 billion-year chemical record on their skin, and that contrast between the calm classical belt and the violent scattered zone opens a door into one of the most extreme regions of the outer solar system, a place where the rules of ordinary Kuiper belt behavior break down entirely. The Kuiper belt proper, the classical region where most well-behaved objects reside, occupies a relatively flat ring from about 30 to 50 times the Earth-Sun distance. Objects there follow stable, predictable orbits. They have been doing so for billions of years. They are the calm neighborhood of the outer solar system. Past that, the neighborhood changes dramatically. The scattered disk is a collection of objects whose orbits have been thrown into chaos. These are Kuiper belt objects that got too close to Neptune at some point in their history and were flung outward into extreme paths. Their orbits stretch far beyond the classical Kuiper belt, sometimes reaching out to over 1,000 times the Earth-Sun distance at their farthest point, before swinging back into the region near Neptune at their closest. The contrast is immediate when you compare the two regions. Classical Kuiper belt objects travel in nearly circular paths, tilted only slightly from the solar system's plane. Scattered disk objects travel in enormous ellipses, often tilted at steep angles. Some scattered disk objects swing so far out that for most of their orbital period, they are farther from the Sun than any planet ever reaches. Then they come screaming back inward, slingshotting around Neptune's region before heading back out into the dark. Neptune is the engine driving this scatter. When an object passes close to Neptune, the planet's gravity can either eject it into a wider orbit or, occasionally, fling it inward toward the Sunday. The scattered disk is essentially a graveyard of objects that had one bad encounter with the solar system's third largest planet and never fully recovered. The objects in the scattered disk are scientifically valuable precisely because of their chaotic orbits. They sample material from a wider range of original solar system locations than classical Kuiper belt objects do. Some scattered disk objects may have formed much closer to the Sun, in the region of the giant planets, before being tossed outward by gravitational interactions during the early solar system's chaotic youth. Studying their composition gives scientists a window into regions of the early solar system that no longer exist in their original form. The scattered disk is also the main source of short-period comets. When a scattered disk object makes its close approach to Neptune's neighborhood, it has a chance of being further nudged into an orbit that crosses the inner solar system. Over time, these nudges funnel a steady stream of icy bodies inward, where they become the comets humans have tracked across the sky for thousands of years. One of the most striking things about the scattered disk is how far its outer boundary extends. Scientists debate exactly where it ends, because some objects with scattered disk-like orbits exist at distances so extreme they begin to blur into a different category entirely. Objects that reach hundreds or thousands of times the Earth-Sun distance start to feel less like Kuiper belt residents and more like something else, something in between the Kuiper belt and the vast, spherical shell of the Oort cloud even farther out. And one specific object sits in exactly that ambiguous territory. It was discovered in 2003 and immediately broke every model scientists had for how the outer solar system was supposed to work. Its orbit made no sense. Its distance made no sense. Its very existence pointed toward forces shaping the outer solar system that had never been accounted for. That object is the reason the story of the Kuiper belt gets significantly stranger from here. November 2003. Astronomer Mike Brown and his team were conducting a sky survey using a telescope at Palomar Observatory in California. They were looking for large, distant objects in the outer solar system. They expected to find more Kuiper belt objects. They found something that did not belong. The object sat far beyond the main Kuiper belt. Its closest approach to the Sun put it at about 76 times the Earth-Sun distance. That alone made it the most distant solar system object ever identified at the time. But the truly strange part was its farthest point. At the outer end of its orbit, this object swings out to roughly 937 times the Earth-Sun distance. To cross its full orbit would take about 11,500 years. Brown's team named it Sedna, after the Inuit goddess of the sea, a figure from mythology associated with the depths of the cold and dark. Sedna is large. Estimates put its diameter at roughly 620 miles, making it one of the bigger objects in the outer solar system. It is reddish, consistent with a tholin-coated surface. It may have a moon, though scientists are still working to confirm that, at its distance, gathering detailed information requires the sharpest telescopes on Earth working at the edge of their capability. But none of those details are what made Sedna famous. What made Sedna famous was its orbit. Specifically, the question of how it got there. Standard models of the outer solar system predicted that no large body should exist in Sedna's orbital neighborhood. The main Kuiper belt extends to about 50 times the Earth-Sun distance. The Oort cloud, the spherical shell of frozen bodies at the solar system's outermost edge, sits at tens of thousands of times that distance. Sedna's orbit put it between these two regions, in a zone that no established model predicted should contain large objects. More troubling still, Sedna's orbit showed no evidence of Neptune's influence. Neptune's gravity shapes the classical Kuiper belt and flings objects into the scattered disk. But Sedna's closest approach to the Sun is already so far beyond Neptune that the giant planet could not have placed it there. At 76 times the Earth-Sun distance, Neptune's gravitational reach is negligible. Whatever put Sedna in that orbit was something else entirely. Scientists proposed several mechanisms. One idea suggested that during the early solar system, our Sun passed close to another star. That stellar encounter, happening when the solar system was young and still forming, could have gravitationally stirred objects in the outer reaches, throwing some into extreme, distant orbits like Sedna's. Another idea proposed that the Sun formed in a star cluster, surrounded by dozens of other young stars, and their combined gravitational influence shaped the outer solar system before the cluster dispersed. A third, more recent idea circles back to Planet 9. A massive unseen planet in a distant orbit could have shepherded objects like Sedna into their current positions over billions of years. All three ideas are under active investigation. All three remain plausible. None has been conclusively confirmed. Sedna sits in its enormous orbit, visiting the inner reaches of its path only once every 11,500 years, offering scientists a brief periodic window to study it before swinging back out into the darkness. And at that farthest point, the darkness Sedna enters is unlike anything in human experience. What that environment actually means, physically, is the next step in understanding just how extreme the outer solar system becomes. Sedna's orbit is not just large, it is almost incomprehensible in its scale. At its farthest point from the Sun, Sedna sits nearly 937 times the Earth-Sun distance away. To put that in a frame a human brain can actually engage with, consider this: the Sun's light takes 8 minutes to reach Earth. At Sedna's farthest point, that same light would take over 5 days to arrive. And even after 5 days of travel, it would arrive so faint that the Sun itself would look like nothing more than a slightly brighter star. You could cover it with a pinhead held at arm's length. At that distance, the Sun provides almost no warmth. Surface temperatures on Sedna drop to around -400 degrees Fahrenheit. To put that number in context, the coldest temperature ever recorded on Earth's surface was around -128 degrees Fahrenheit in Antarctica. Sedna is roughly 3 times colder than the coldest place on our planet. The cold there is so complete that gases that flow freely in Earth's atmosphere freeze into solid sheets and stay that way for thousands of years. Sedna spends the overwhelming majority of its 11,500-year orbit near that far end. It loiters in the darkness for thousands of years at a stretch, barely moving relative to the star it orbits, crawling through space in near total blackness before its orbit's geometry slowly, over millennia, curves it back toward the Sunday. There is something almost conceptually disorienting about an orbit on that scale. Earth completes one orbit every 365 days. Sedna completes one orbit every 11,500 years. When Sedna was last at its current position in its orbit, humans on Earth had not yet invented writing. We were living in small settlements, using stone tools, thousands of years before the first Egyptian pyramid. By the time Sedna returns to where it is now, human civilization will have either solved or failed to solve every challenge currently facing our species. That timescale is not just philosophically strange, it has practical scientific consequences. Sedna only enters the relatively close portion of its orbit for a brief window every 11,500 years. Right now, by a remarkable coincidence in astronomical terms, Sedna is near its closest approach. Scientists have a window, measured in centuries, to study it before it swings back out into the darkness and becomes essentially unobservable for thousands of years. That window is closing, slowly by human standards, but closing. Sedna is moving outward. Each decade it spends near closest approach will not come again for over 11,000 years. The urgency scientists feel about studying it is real and measurable. What Sedna carries on its surface, frozen there since the earliest days of the solar system, may contain direct chemical evidence of what the outer solar system looked like before any of the planets formed. It is a frozen record from an era so early in cosmic time that even the Sun was still settling into its mature state, and the forces that placed Sedna in that extreme orbit, whatever they were violent enough to leave traces in the gravitational structure of the entire outer solar system, traces that point back to a single catastrophic event, one that involved something passing close to our solar system from outside. The outer solar system carries scars. Sedna is one of them. Its impossible orbit, sitting in the gap between the Kuiper belt and the Oort cloud, in a region no model predicted should contain large objects, is a gravitational fingerprint. Something left it there, something with enough mass and gravitational reach to reshape the outer solar system on a grand scale. And the leading suspect is a star that passed close to our Sun billions of years ago. Stars are not fixed in space, they move. The Milky Way contains hundreds of billions of stars, all orbiting the galaxy's center at different speeds and on different paths. Close encounters between stars happen over the lifetime of a solar system. The chances of another star passing within a few light years are significant. At close enough distances, even a brief stellar encounter, two stars slipping past each other at tens of thousands of miles per hour, can have lasting gravitational consequences. Scientists call these events stellar flybys, and the evidence suggests that one, or possibly more, happened to our solar system when it was young. Here is how the math works. When a star passes close enough, its gravity reaches into the outer solar system like a large hand running through a tray of marbles. Objects in the outermost reaches of the solar system, the ones barely held by the Sun's gravity to begin with, get tugged sideways. Some get flung outward entirely and leave the solar system. Others get pulled into new orbits with different shapes and orientations, their original circular or mildly elliptical paths bent into the extreme elongated loops we see in objects like Sedna. Simulations of stellar flybys produce exactly the kind of orbital distribution scientists observe in the outermost solar system. When a passing star of the right mass, at the right distance, is plugged into a model of the early solar system, objects in the outer zone end up scattered into a range of orbital shapes and orientations that match what telescopes actually see today. The timing also lines up. The early solar system almost certainly formed inside a stellar nursery, a dense region of space where hundreds or thousands of stars form close together from the same gas cloud. In these environments, stellar encounters are far more common than in the current neighborhood. Our Sun eventually drifted away from that birth cluster, but during the period when it was still embedded in that crowded nursery, close stellar encounters would have been relatively frequent. One simulation identified a candidate encounter, a star about 8/10 the mass of our Sun, passing within roughly 800 times the Earth-Sun distance about 4 billion years ago. That flyby, in the model, produces an outer scattered population of objects with orbital properties very similar to Sedna's. The math is compelling. The star has not been identified, but it would have long since moved away to a different part of the galaxy, untraceable now. The implications of a stellar flyby are significant beyond just explaining Sedna. If a passing star stirred the outer solar system, it would have sent a wave of displaced objects inward. Some of those objects may have contributed to the late heavy bombardment that hammered the inner solar system roughly 4 billion years ago, reshaping the surfaces of the Moon, Mars, and Earth in a period of intense impact that lasted millions of years. The passing star that disturbed Sedna's orbit may be indirectly responsible for some of the craters on the Moon visible with the naked eye tonight. The outer solar system holds these kinds of ancient records. Every strange orbit is a clue, and when scientists began assembling the full picture of how the solar system formed and evolved, What they found was evidence of a history far more violent, far more dynamic, and far more interesting than anyone expected. The solar system was not built calmly. It was assembled through 4.5 billion years of catastrophic events, near misses, gravitational wrestling matches between planets, and mass ejections of material from one zone to another. The Kuiper belt is what survived all of that, and what survived is only a fraction of what was originally there. In the earliest phase of solar system formation, the outer region beyond Neptune was far more densely populated than it is today. Scientists estimate that the original mass of material in the zone that became the Kuiper belt was roughly 20 to 30 times the mass of Earth, possibly more. Today, the entire Kuiper belt contains less than 1/10 the mass of Earth. Something took away more than 90% of the original material. That is a staggering loss. Imagine a city with 30 million residents that somehow shrank to fewer than 3 million, with no obvious disaster to explain where everyone went. Scientists call this the mass deficit of the Kuiper belt, and explaining it has driven some of the most ambitious planetary modeling of the past 30 years. The process that removed all that mass was not a single event, it was a cascade. In the early solar system, the giant planets were closer together and their orbits were more compact. Jupiter, Saturn, Uranus, and Neptune formed in a crowded inner configuration before something changed. Gravitational interactions between the giants themselves caused their orbits to shift. The planets migrated. Some moved inward, some moved outward. Neptune, specifically, is believed to have formed closer to the Sun than it currently sits and then migrated outward over millions of years. As it moved outward, it swept through the original outer disk like a plow through snow. Objects in its path got flung. Some went into the inner solar system, joining the wave of impacts during the late heavy bombardment. Some got ejected from the solar system entirely. Some ended up in extreme, scattered orbits, and a fraction settled into the resonant and classical Kuiper belt we see today. The orbital scattering was so thorough that the surviving Kuiper belt objects represent a highly selected sample. The ones that remained did so because they happened to be in specific orbital configurations that Neptune's migration left relatively stable. Pluto, in its 2-to-3 resonance with Neptune, survived because that ratio protected it. Many other objects at similar distances were ejected. This picture of a violent early outer solar system reshaped by migrating giant planets is called the Nice model, named after the city in France where a team of scientists developed it in the early 2000s. The Nice model has successfully explained several features of the outer solar system that older models could not, including the orbital distribution of Kuiper belt objects, the late heavy bombardment, and the capture of some irregular moons by the outer planets. It paints a picture of a solar system that was, for its first billion years, far more dangerous and chaotic than the relatively stable system we inhabit today. The Kuiper belt is the archive of that chaos. Every object out there is a survivor, and the scars of that early violence are written in their orbits, their compositions, and the very fact that so few of the originals remain. What happened to the missing mass, and how its loss shaped Earth's ability to exist, is tied directly to the same giant planet migrations that left the Kuiper belt in its current depleted state. But the story of that depletion goes even deeper than orbital mechanics. In the early 2000s, a group of scientists at the Nice Observatory in France sat down with a computational model of the early solar system and ran it forward in time. What came out of their simulation was so surprising that it initially met serious skepticism from the planetary science community. But over the following years, as the model's predictions matched more and more of what telescopes actually observed, it became one of the most influential ideas in modern planetary science. The Nice model starts with a specific setup. In the early solar system, roughly 4 billion years ago, Jupiter, Saturn, Uranus, and Neptune all sat in a more compact formation than they do today, with Neptune about half as far from the Sun as it currently orbits. Between them, and the Kuiper belt region sat a dense disk of small, icy bodies, the original material of the outer solar system. This disk was far more massive than the Kuiper belt is now. For the first several 100 million years, the system stayed relatively stable. Then the gravitational interactions between the giant planets began to slowly push them into new orbital ratios. Saturn and Jupiter, moving in a particular gravitational relationship with each other, eventually crossed a critical threshold. Their gravitational rhythms synchronized in a way that sent ripples through the entire outer solar system. The result was an instability. Jupiter moved slightly inward. Saturn, Uranus, and Neptune all moved outward. The outward movement of Uranus and Neptune drove them into the disk of small icy bodies. They scattered objects in all directions. Material that had been sitting quietly in the outer disk for hundreds of millions of years suddenly got thrown everywhere. A wave of icy objects plunged into the inner solar system. This wave is what scientists believe caused the late heavy bombardment, the period of intense impacts that scarred the moon's surface, hammered early Earth, and even appears to have reshaped Mars. The moon's cratered face is essentially a record of the NICE model's most violent moment. Neptune kept moving outward, continuing to scatter the outer disk as it went. The objects it did not eject settled into new orbits, shaped by the resonances of Neptune's final resting position. The 2 to 3 resonance that Pluto now occupies, the resonances that the other classical Kuiper belt populations sit in, all formed during this period of Neptune's outward migration. What the NICE model explained that previous models could not was the specific distribution of Kuiper belt objects across different orbital families. The ratios of objects in different resonances, the inclination of their orbits, the ratio of classical to scattered objects, all emerged naturally from the model's simulation of Neptune's migration. It was the first model that could reproduce the Kuiper belt's actual structure from first principles. There is a detail in the NICE model that has personal stakes for Earth. During the instability phase, some simulations show Jupiter briefly moving close enough to the inner solar system to gravitationally interact with the rocky planets. In some simulation runs, Mars gets knocked into a very different orbit. In others, Earth comes close to being destabilized. The solar system we live in today, with stable orbits for Mercury, Venus, Earth, and Mars, is one specific outcome of a process that could have gone differently. Our existence on Earth may have required the giant planets to arrange themselves just right, and the Kuiper belt, in its current depleted, survivor-populated state, is the record of exactly how close that arrangement came to failing. What came after the NICE model's violent phase, the slow resealing of the outer solar system into something almost calm, left behind a few objects with behaviors stranger than anything the NICE model alone can explain. The Kuiper belt today is a ghost of what it once was. The numbers make that clear. Scientists estimate that the original outer disk contained somewhere between 20 and 30 Earth masses of material. The current Kuiper belt holds less than 1/10 of one Earth mass. More than 98% of the original material is gone. That loss happened over a specific window of time, roughly between 3.5 and 4 billion years ago, during the period when the giant planets were migrating and the NICE model instability was playing out. The mechanism was Neptune. As the planet moved outward through the original outer disk, it acted like an enormous gravitational vacuum, throwing objects in every direction. Objects ahead of Neptune's path were flung outward into scattered disk orbits or ejected from the solar system entirely. Objects behind it got swept into resonances or pushed inward. The ejected objects are simply gone. They left the solar system on hyperbolic trajectories, meaning paths so steep they escape the sun's gravity entirely and travel outward forever into interstellar space. These former Kuiper belt objects are now drifting between the stars, untethered, moving through the galaxy as free-floating interstellar bodies. Scientists suspect there are enormous numbers of these objects scattered through interstellar space, former members of planetary systems ejected during their system's early violent phases. In 2017, astronomers detected an object passing through the inner solar system on an unambiguously interstellar trajectory. It came from outside the solar system, swung around the sun, and left again, never to return. Scientists named it Oumuamua. Its shape, elongated and flat in a way that no known solar system body matches, sparked intense debate about its origin. Some researchers proposed it was a piece of rocky or icy debris from another stellar system, ejected during that system's own early instability phase, equivalent to one of our own ejected Kuiper belt objects drifting through a foreign solar system. The discovery of Oumuamua suggested that the ejection of planetary building material during system formation is common. Our solar system ejected enormous quantities of material during Neptune's migration. Other systems did the same. The galaxy is seeded with these ancient wanderers, free-floating remnants of planetary formation events scattered across billions of light years. The objects that remained in our Kuiper belt after Neptune's migration were the survivors. They found stable niches, orbital configurations that Neptune's passage left relatively intact. But even the survivors show evidence of the violence they endured. Their orbits cluster in specific families corresponding to Neptune's resonances. The gaps between those families correspond to regions where Neptune's influence was most disruptive, zones that were cleared out almost completely during the migration. The fact that anything survived at all is a consequence of the specific geometry of Neptune's migration path. Small changes in how Neptune moved could have swept the outer disk even more thoroughly. A slightly different migration could have eliminated the Kuiper belt entirely, leaving the outer solar system nearly empty. The Kuiper belt exists because Neptune happened to stop where it stopped, in an orbit that left specific stable niches intact. And some of the objects sitting in those surviving niches have properties that make even the story of Neptune's migration look simple by comparison. Objects with atmospheres that freeze and thaw on seasonal cycles stretching decades long, with alien weather powered by nothing more than the feeble warmth of a distant Sunday. That alien meteorology, playing out on frozen worlds at the edge of the solar system, is one of the most unexpected things scientists have discovered out there. Pluto breathes. Scientists confirmed this during the New Horizons flyby, and it remains one of the most unexpected discoveries to come out of Kuiper belt exploration. An object smaller than the continental United States, sitting billions of miles from the sun in temperatures approaching -360 degrees, maintains a thin but real atmosphere, and that atmosphere does something that no atmosphere on Earth or any other planet does in quite the same way. It completely freezes to the surface during winter and reforms from solid ice during summer. Pluto's seasons are extreme. Because Pluto's orbit is highly elliptical, it swings from roughly 29 times the Earth-Sun distance at its closest to nearly 49 times that distance at its farthest. That difference in distance from the Sun produces enormous changes in how much solar energy Pluto receives. At closest approach, slightly more heat reaches the surface. Nitrogen ice on the sun-facing side sublimates, turning directly from solid to gas, building up the thin atmosphere. At farthest approach, the temperature drops further, the gas freezes back to solid, and the atmosphere collapses entirely. One full Pluto year lasts 248 Earth years. Pluto has not yet completed one full orbit around the Sun since its discovery in 1930. The atmospheric cycle, the annual freezing and thawing of the atmosphere, plays out over centuries from a human perspective. What Pluto's atmosphere actually contains is remarkable. Primarily nitrogen, the same gas that makes up about 78% of Earth's atmosphere, but also methane and carbon monoxide in smaller quantities. These gases interact with each other and with incoming solar radiation to produce a haze layer, actually multiple haze layers, that New Horizons photographed above Pluto's surface. These haze layers are where tholins form, those complex, reddish organic compounds that slowly rain down onto the surface over geological timescales. Eris, the large Kuiper belt object that triggered Pluto's reclassification, also appears to have a seasonal atmosphere. Scientists studying Eris as it passed in front of a background star measured subtle effects consistent with a thin nitrogen atmosphere. Like Pluto's, this atmosphere likely collapses to the surface during the long, cold period of its orbit and partially regrows when Eris swings closer to the Sunday. The possibility of atmospheric activity on Kuiper belt objects overturned an assumption scientists had held for decades. Conventional thinking held that any atmosphere at such distances from the Sun would be permanently frozen solid, locked to the surface, with no possibility of gas phase activity. Pluto proved that wrong, and Eris extended that lesson to objects even farther out. The implication for planetary science broadly is that the boundary between active and dead worlds is not cleanly defined by distance from a star. Even at the solar system's frozen edge, thermodynamic cycles can operate. Weather happens. Slow, alien, measured in centuries rather than days, but real. Nitrogen clouds may drift over Pluto's mountains. Methane frost may be accumulating right now on Eris's surface in patterns shaped by its rotation and seasonal tilt. These are alien weather systems in the darkness at the edge of the solar system. And the object that brought all of this into sharpest focus, the one whose discovery forced the scientific community to reconsider everything from planetary definition to the scale of the Kuiper Belt's population, was a world that spent years being considered a potential 10th planet. Its story is one of the most dramatic in modern planetary science. January 5, 2005. Mike Brown and his colleagues at Caltech were reviewing images from their sky survey when a point of light caught their attention. It was moving against the background of stars, which meant it was a solar system object, but its motion was slow, very slow. Slow motion in the sky means one thing: the object was far away. They measured its distance. It sat at about 97 times the Earth-Sun distance. That made it the most distant solar system object ever discovered at that point. But the size estimate is what stopped the room. Based on its brightness and distance, the object appeared to be approximately the same size as Pluto. Some early measurements suggested it might even be slightly larger. Brown nicknamed it Xena at first, after a popular television character. Later, it was formally named Eris, after the Greek goddess of conflict and strife. The name was chosen deliberately. Eris caused conflict that reshaped planetary science. The discovery created a logical trap. If Pluto was a planet, Eris had to be one too. They were nearly identical in size. They occupied similar regions of the outer solar system. Both had moons. Both had reddish, complex surfaces. Calling Pluto a planet while classifying Eris as something else had no scientific justification. Either both were planets, or neither was. The International Astronomical Union, the organization responsible for classifying celestial bodies, met in August 2006 to resolve the debate. After heated discussion, they established the dwarf planet category and placed both Pluto and Eris inside it. Pluto lost its planet status. The public backlash was significant. Mike Brown received strongly worded letters for years. But what the reclassification revealed was more important than any title. Eris was the tip of a population. If objects the size of Pluto and Eris existed in the outer solar system, statistical models predicted there should be dozens more at similar sizes that had simply not been found yet, either too dark, too distant, or too far from where telescopes had been pointed. The Kuiper belt was far more populated with large objects than anyone had assumed. Eris itself has a single known moon, Dysnomia. By measuring Dysnomia's orbital period and distance from Eris, scientists calculated Eris's mass with precision. The result was a shock. Eris is about 27% more massive than Pluto, despite being almost exactly the same size. That density difference suggests Eris contains a much higher proportion of rock relative to ice than Pluto does. Two objects nearly identical in appearance, separated by a significant gulf in internal composition. That compositional difference points to formation in different parts of the original outer disk. Eris may have formed closer to the Sun in the original protoplanetary disk, and been scattered outward later, picking up a denser, rocky composition from the region where it formed. Pluto, forming farther out, incorporated more ice and ended up lighter. Eris currently sits at about 97 times the Earth-Sun distance, but its orbit is highly elliptical. At its closest approach, it swings in to about 38 times that distance. At its farthest, it reaches about 98 times. Its full orbital period is about 559 Earth years. Right now, it is near its farthest point, which is why it is so difficult to study in detail. As it swings back inward over the coming centuries, opportunities to study it will improve. What remains locked in its ice, frozen since before Earth existed, keeps researchers watching closely. And what that chemistry might mean for the origin of life on Earth leads directly into the most profound question the Kuiper Belt raises for our own existence. 4 billion years ago, Earth was a very different place. The surface was hot, volcanic activity was intense, the atmosphere was thick with gases that would be lethal to any life that exists today. Liquid oceans were just beginning to form as the surface cooled enough for water to stop evaporating instantly, and something was falling from the sky constantly. Comets, fragments from the Kuiper Belt and beyond, nudged inward by gravitational interactions during the solar system's violent early period. They hit Earth continuously during the late heavy bombardment. Their impacts released enormous energy. They reshaped the surface. They also delivered something. Scientists examining Kuiper Belt comets that have entered the inner solar system and passed close enough to study found a consistent chemistry inside them. Water ice, yes, but also complex organic molecules, carbon chains, simple sugars, and amino acids. Amino acids are the building blocks of proteins. Proteins are the machines of life. Every enzyme, every structural component of a cell, every mechanism that allows a living organism to function is built from proteins. And proteins are assembled from chains of amino acids. Find amino acids in a comet, and you find the raw materials from which life builds itself. In 2006, a sample return mission brought back material from a comet called Wild 2. Scientists analyzed the samples and found glycine, the simplest amino acid. This was not contamination from Earth. Researchers took extensive precautions and ran multiple verification tests. The glycine was genuinely extraterrestrial. It formed inside a comet in space, from chemistry driven by radiation and the harsh environment of the early solar system. The discovery opened a serious scientific debate that continues today. Did life on Earth develop entirely from chemistry that originated on Earth? Or did comets from the Kuiper Belt deliver a significant portion of life's starter kit? Or both? The hypothesis that life's ingredients arrived from space has a name: panspermia, from Greek roots meaning seeds everywhere. The strongest version of panspermia suggests that living organisms themselves travel between star systems. Scientists consider that version unlikely, given how hostile space is to living cells. But the weaker version, that organic molecules capable of producing life form in space and get delivered to habitable planets, has gathered substantial evidence behind it. Early Earth's oceans would have been a chemical mixing bowl. Amino acids from Kuiper Belt comets, arriving by the billions of tons over millions of years of bombardment, would have dissolved into those oceans. In warm, shallow water, amino acids can spontaneously form into longer chains under the right conditions. Those chains can fold. Folded chains begin to take on the properties of primitive proteins, and from primitive proteins, the path to the first self-replicating molecules, the earliest ancestors of life, becomes shorter. Scientists have run these chemistry experiments in the lab. Amino acid-rich solutions, subjected to conditions resembling early Earth's tide pools or volcanic vents, do produce more complex molecules. The chemistry works. The question is whether it happened, and how much the Kuiper Belt contributed. The comets delivered water too. Earth's current oceans may be partly composed of water that arrived from the outer solar system. The hydrogen isotope ratio in Earth's ocean water matches the isotope ratio found in some Kuiper Belt comets, a chemical fingerprint suggesting a genuine ancient connection. We may be drinking water that was frozen in the Kuiper Belt for billions of years before a comet carried it here. Every ocean, every rain cloud, every glass of water on Earth may carry chemistry from the edge of the solar system, and that chemistry arrived alongside something far more destructive. Scientists who study planetary defense do not spend much time worrying about asteroids from the main belt between Mars and Jupiter. They are monitored, their orbits are mapped, the dangerous ones are tracked. The threat, while real, is manageable with enough warning. The objects that keep planetary defense researchers most alert at night are the ones from the outer solar system. Long-period comets, arriving from the Kuiper Belt or beyond, present a specific and deeply uncomfortable problem. They come from the dark, they move fast, and by the time they become visible, the warning window can be uncomfortably short. A large Kuiper Belt object entering the inner solar system for the first time would travel at speeds between 30 and 40 miles per second relative to Earth. That is over 100,000 miles per hour. For comparison, a typical near-Earth asteroid might cross Earth's orbital zone at around 12 miles per second. A Kuiper Belt object is roughly 3 times faster, and speed is not just a detail. Kinetic energy scales with the square of velocity. An object moving 3 times faster carries 9 times the destructive energy at the moment of impact for the same mass. A Kuiper Belt object with a diameter of around 6 miles, similar in size to the impactor that ended the Cretaceous period 66 million years ago and wiped out the non-avian dinosaurs, striking Earth at 100,000 miles per hour, would release energy measured in billions of nuclear weapons worth of force. The impact would vaporize everything within hundreds of miles instantly. The shockwave would flatten forests and structures across thousands of miles. Dust and debris thrown into the upper atmosphere would block sunlight globally for years. The resulting famine would threaten nearly every complex life form on the planet. But a 6-mile diameter object is not even close to the largest things sitting in the Kuiper Belt. Pluto is about 1,400 miles across. Eris is nearly the same. Even much smaller Kuiper Belt objects, ones in the 100-mile diameter range, would be extinction-level threats by a wide margin. The specific problem with outer solar system objects is detection time. Near-Earth asteroids are discovered years or decades before any potential encounter, giving time for mission planning and potential deflection. A long-period comet from the Kuiper Belt might only become bright enough to detect when it is already inside Jupiter's orbit. At that point, depending on its exact trajectory, the time before a potential Earth impact could be as short as months. Current deflection technology, primarily the kinetic impactor approach, tested by NASA's DART mission in 2022, requires years of lead time to be effective. Against a comet with months of warning, that approach provides essentially no protection. Against a very large object, even years of warning would be insufficient with current technology. Scientists are working on this problem. Proposals include space-based telescopes specifically designed to survey the outer solar system for incoming objects earlier in their trajectories. Others involve nuclear deflection concepts for large, fast-moving threats. But no dedicated outer solar system early warning system is fully operational today. The probability of a large Kuiper Belt object striking Earth in any given human lifetime is extremely low, but the Kuiper Belt contains billions of objects. Over geological timescales, the inner solar system has been struck repeatedly. It will be struck again. The question is when. And the honesty is that our current ability to see the threat coming is limited by the very darkness that makes the Kuiper Belt so hard to study in the first place. Here is an uncomfortable fact about the Kuiper Belt. Scientists do not know how many objects are in it. They have estimates. They have population models built from statistical extrapolation, but a complete inventory is beyond the capability of any telescope currently in operation. The problem is darkness and distance combined. A Kuiper Belt object at 40 times the Earth-Sun distance receives about 1,600 times less sunlight than Earth does. That object reflects only a fraction of the sunlight it receives, depending on how dark or bright its surface is. The light that bounces back then has to travel 40 times the Earth-Sun distance again to reach a telescope on Earth. By the time it arrives, the signal is extraordinarily faint. The faintest objects current ground-based telescopes can detect at Kuiper belt distances are somewhere in the range of 100 to a few hundred miles across. Anything smaller than that simply disappears into the background noise, but the Kuiper belt likely contains billions of objects smaller than 100 miles across. Those billions are effectively invisible to us. This is not a minor gap in the inventory. The missing small objects carry important scientific information. Their size distribution tells scientists about the history of collisions in the belt. Their composition tells scientists about the chemistry of the early solar system at different distances from the Sunday. Their orbits would tell scientists about the gravitational forces that have shaped the outer solar system over billions of years. Beyond the detection limit problem, there is also an observational coverage problem. Surveys of the Kuiper belt have focused on specific regions of sky. The most productive surveys concentrated along the ecliptic, the plane of the solar system, because that is where most Kuiper belt objects are expected. But Kuiper belt objects with high orbital inclinations, ones traveling at steep angles to the ecliptic, could sit in regions of sky that have received far less survey attention. Scientists have a term for this: observational bias. It means the population of Kuiper belt objects scientists know about is skewed toward whatever is easiest to detect. Bright objects at low orbital inclinations in heavily surveyed regions dominate the known catalogue. Dark objects, small objects, and objects at high inclinations in poorly surveyed sky are systematically underrepresented. The implications for Planet 9 are relevant here. If the sky coverage of outer solar system surveys is uneven, then the clustering of distant Kuiper belt objects that suggests a massive hidden planet could partly reflect where scientists have been looking rather than a genuine physical grouping. This is the observational bias objection that Planet 9 skeptics raise. More complete sky coverage would either confirm the clustering or reveal it as an artifact of where telescopes have been pointed. All of this changes with one instrument currently coming online. A telescope designed to photograph the entire visible sky every few nights, accumulating a dataset of the outer solar system that will dwarf everything that came before it. When that instrument turns its eye to the Kuiper belt, the number of known objects is expected to multiply dramatically, and what that survey reveals will either confirm the broad outlines of what scientists already believe about the outer solar system, or overturn them entirely. On a mountaintop in the Chilean Andes, at an altitude of about 8,800 feet, a telescope finished construction and began its survey operations. It is called the Vera Rubin Observatory, named after the astronomer who discovered evidence for dark matter by studying how galaxies rotate, and its primary mission is to photograph the entire visible sky, repeatedly, over 10 years. The telescope carries an 8.4-meter primary mirror, one of the largest in the world for a survey telescope. Its camera contains over 3 billion pixels, making it the largest digital camera ever built. Every night it operates, it photographs the sky in a mosaic pattern, returning to every point in the visible sky roughly every few nights. Over 10 years, it will build a time-lapse record of the entire southern sky, with a depth and consistency that no previous survey has approached. For Kuiper belt science specifically, the Vera Rubin Observatory changes the game fundamentally. Current surveys have identified somewhere around 3,000 Kuiper belt objects total, accumulated over decades of observation with multiple different telescopes. Scientists estimate that the Vera Rubin Observatory will find between 40,000 and 100,000 new Kuiper belt objects within its first few years of operation. That jump in sample size, from thousands to tens of thousands or hundreds of thousands, is transformative for the kind of statistical analysis scientists need to answer the biggest open questions about the outer solar system. The Planet 9 question gets addressed directly. With a vastly larger sample of distant Kuiper belt objects, scientists will either confirm that the orbital clustering is real across a complete, unbiased population, or they will find that the clustering disappears once observational bias is removed. Either answer is valuable. Confirmation would make the case for Planet 9 dramatically stronger. Refutation would force scientists to find a different explanation for the orbital patterns they currently see. The mass of the Kuiper belt becomes measurable with new precision. The size distribution of Kuiper belt objects, how many exist at each size range, holds information about the collision history of the belt and the conditions in the early outer solar system. With hundreds of thousands of objects in the catalogue instead of thousands, that distribution can be mapped with far more accuracy. The observatory will also reveal objects in the scattered disk and beyond with new sensitivity. Sedna-like objects, those extreme outliers sitting in the gap between the Kuiper belt and the Oort cloud, may be more numerous than currently suspected. If the Vera Rubin Observatory finds dozens of Sedna-like objects instead of the handful currently known, it strengthens the case for whatever mechanism placed them there, whether stellar encounters, Planet 9, or something else. The survey's time-lapse nature adds another dimension. By returning to the same patch of sky every few nights, the observatory catches objects in motion. Objects moving slowly against the background stars are far away. Objects moving quickly are nearby. By tracking motion, scientists can determine approximate distances and orbits for every detected object, building a three-dimensional map of the outer solar system that has never existed before. When that map is complete, or even partially complete, it will represent the most detailed picture of the Kuiper belt in human history, and that picture will inevitably reveal things scientists have not predicted. Every time a new instrument has turned its gaze to the outer solar system, something unexpected has appeared. The Vera Rubin Observatory will almost certainly continue that tradition, and whatever it finds at the absolute outer edge of the Kuiper belt, where that belt dissolves into something else entirely, may be the most important discovery yet. Stand at the outer edge of the Kuiper belt and look outward. Behind you is everything humans have ever explored. Every planet, every moon, every asteroid visited by a spacecraft, every comet studied up close. All of it sits inward toward a sun that, from here, looks just slightly brighter than the other stars. Ahead of you is something scientists have never directly visited: a vast, spherical shell of frozen objects surrounding the entire solar system at distances ranging from a few thousand to over 100,000 times the Earth-Sun distance. The Oort cloud, the outermost structure of the solar system, a reservoir containing trillions of frozen bodies in orbits so large, so slow, so distant that they barely register as part of the solar system at all. Between the Kuiper belt and the Oort cloud lies the region where Sedna drifts. Scientists call it the inner Oort cloud, though the name is contested. It is poorly understood and barely observed. It sits in a zone that no spacecraft has reached and no current telescope can survey completely. The Vera Rubin Observatory will begin to illuminate this region, but full understanding is decades away. At the very outer boundary of the Oort cloud, the sun's gravitational grip becomes barely stronger than the combined gravitational pull of the galaxy around it. Objects there sit in orbits so loosely bound that a passing star, a nearby molecular cloud, or even the general tidal force of the Milky Way can disturb them, sending them falling inward toward the sun over millions of years. These are the long-period comets, the ones that arrive from seemingly nowhere on trajectories that take tens of thousands of years to complete. And just beyond the Oort cloud's outer edge, interstellar space begins. The boundary is not a wall, it is a gradual transition. The solar wind, the stream of charged particles flowing from the sun, extends out to a boundary called the heliopause, roughly 120 times the Earth-Sun distance. The Voyager spacecraft crossed that boundary, becoming the first human-made objects to enter interstellar space. But even the heliopause is far inside the Oort cloud, which extends much farther. The solar system is far larger than the reach of the solar wind. The Kuiper belt is the last named, partially mapped, somewhat understood structure before all of that vast outer territory. It is the edge of the surveyed map. Everything beyond it is here, there, be Dragon's territory, in the most literal astronomical sense. What will scientists find when they finally map the Kuiper belt completely and begin to probe the regions beyond it? The Vera Rubin Observatory data, combined with future dedicated outer solar system missions, will begin to answer that. Planet 9, if it exists, will eventually be found or definitively ruled out. Sedna-like objects will either prove common or rare. The inner Oort cloud will begin to reveal its population. Every discovery in the outer solar system for the last 30 years has surprised scientists. The Kuiper belt was larger than predicted. Its objects were more chemically complex than expected. Pluto had mountains and a heart and evidence of possible liquid water. Arakoth showed that planet formation was gentle. Sedna showed that the outer solar system was disturbed by forces scientists had not accounted for. The pattern of discovery out there is consistent. The outer solar system is stranger than the models. It contains more, does more, and means more than the clean, simple picture allows. The Kuiper belt is the edge of our current understanding, and it is already full of things that rewrite textbooks. What sits just beyond it, in the dark, waiting to be found, may be stranger still.